Imagine a boat floating in the water. As the wind picks up, it pushes the sail, accelerating the boat. The boat gets faster and faster until its speed exactly matches the wind. But at this point, the wind can't push the sail anymore. I mean, if you imagine it from the frame of reference of the boat, there's no longer any apparent wind. There's no air moving over the boat because the air and the boat are moving together at the same speed. So a sailboat going directly downwind can only match the speed of the wind, never exceed it, even if there's no drag. That sailing at some angle to the wind, a sailboat can go enough faster that its resulting velocity directly downwind is faster than the wind itself. In other words, it can beat a balloon that is just drifting on the wind.
If the Earth were a cylinder instead of a sphere, I could have a sailboat on a continuous downwind tack. The wind's going along the Earth, this cylindrical Earth, and the sailboat is just spiraling its way down. If I put two sailboats, one on either side, they can both do this. Well, that's a prop.
Effectively, their sails make a propeller that is traveling down this Earth faster than the wind itself. You don't actually need aerodynamics. Here I have a little cart with a big wheel that rolls on two smaller spools. And what I'm going to show is that when you have two media moving relative to one another, well then if this car is in contact with both media, it can actually move faster than their relative velocity. So as I push the board to the right, you can see that the car goes down the board faster than the board is moving. If you look carefully, you'll see that the big wheel isn't turning the way that the board is pushing it. It's actually rotating in the opposite direction. That's just like the propeller on Blackbird, which pushes back against the air, and that's how it's able to go faster than the wind downwind.
Let's do it again from the front so you can see the interaction between all of the gears. Here's the 3-to-1 gear ratio. Let's count the rotations of the orange handle. 1 rotation, 2, and 3. And this is the 1-to-3 gear ratio. So you can see just by spinning the blue handle, the orange handle will spin 3 times. This is the 1-to-2 gear ratio. We also have the 2-to-1 gear ratio. So every time the small orange handle spins twice, the outer copper handle only spins once in the opposite direction. And this is the 3-to-2 gear ratio. You're probably getting the idea here. There are a lot of different combinations. And finally, the 2-to-3 gear ratio.
It's like having a fan on your cart. So of course, even in still air, having a fan on the cart will blow you forwards. And so if you were to look at a profile of the air in a stationary reference point, you would see that the wind behind the propeller would be moving more slowly downwind than all the other wind. That's because this propeller has taken some of the energy out of that wind and converted it into the kinetic energy of this cart. Even when this is moving forward faster than wind speed, the propeller can still push the air backwards, slowing down that tailwind and taking some of that wind's energy, converting it into the kinetic energy of this vehicle. The way it works is the wind pushes it from behind, and just because it's a bluff body, it's just an object sitting out in the desert, it starts to roll forwards a little bit. Now that causes the wheels to turn, and they are geared to the propeller in such a way that they turn it opposite the direction the wind is pushing it. So rather than this propeller operating like a windmill, it spins like a fan, pushing air backwards, and that's what drives the craft forwards. The propeller doesn't work like most people think. It's not working like a windmill. It doesn't turn the way the tailwind is pushing it. Instead, it turns in the opposite direction, working like a fan to push air backwards. This fan is powered by the wheels, which are connected to the propeller by a bike chain. So at wind speed, the car can keep accelerating because the wheels turn the fan, which blows air back, generating forward thrust. The wheels are going so much faster over the ground than the propeller is moving through the air, so the thrust force can actually be larger. So what about the treadmill tests? These are conducted in still air. By moving the ground backwards, you're simulating a perfectly steady tailwind. And if you hold the car stationary on the treadmill, well, that's equivalent to the car going exactly wind speed. Now, if the car can move forward on the treadmill, that shows it can accelerate faster than the wind.
And even physics professors were arguing that the treadmill wasn't a good analog of the real world. And I'm like, literally day one physics is inertial frames, right? It doesn't matter if you're moving or the air's moving.
A 1-to-1 gear ratio in a transmission is called a direct drive, where the engine is spinning exactly the same speed as the output.
The ratio of the propeller pitch to the wheel circumference. Ratio of these two factors, the propeller distance over the wheel distance, is something that the inventor of this craft calls the vehicle speed ratio, or VSR.
Propellers with lower pitch angles to try those out.
Still a pretty serious tug, hey?
Well,
It's not feeling like it's gonna push itself forward.
And that was the problem with my first two carts, other than the fact that the wheels fell off. But they never would have worked anyway, because the VSR was like 1.5 or higher.
We're going straight downwind. What have I got? 6 miles an hour. The string is just dangling.
we're 5 or 6 miles an hour, and I'm like, damn, because he's almost exactly wind speed.
Yeah.
5 or 6 miles an hour is just not enough to get you
Right.
past there.
I needed just like that extra few miles an hour.
It's kind of the absolute minimum. 10 is pretty healthy.
Yeah, yeah. still a pretty serious tug, hey?
Well,
It's not feeling like it's gonna push itself forward. While steering with my right hand, I have to control the pitch of the propeller blades with my left hand. I'm going faster than the wind.
Slow down, Derek. Full tack, full tack.
Oh,
Nope. At the wheels, power is input into the system by the ground moving underneath the car. The power generated is the force of the ground on the wheels times the velocity of the car. At the propeller, work is done on the air as the propeller pushes it backwards. The power out equals the force of the prop on the air times the speed of the car minus the speed of the wind. The prop is going slower through the air due to the tailwind. And if we assume no losses, then the power in at the wheels equals the power out at the propeller. From this equation, we can see that the force at the propeller will be greater than the force at the wheels. And since the propeller is pushing air back, the air applies an equal and opposite force forward on the prop. This is the thrust force, which will be greater than the backwards force on the wheels. Even though I didn't have a speedometer in the car for my runs, someone on Twitter pointed out that we could use the rotation of the back wheel to determine the speed from the video footage. This shows that even after the telltale flips backwards, the car keeps accelerating. Another thing I want to point out is that if wind gradient or gusts were the reason that the car travels faster than the wind, well, you'd expect the telltale to jump around or at least not point straight back at me. But it consistently does for over 30 seconds until I had to hit the brakes to avoid crashing into parked vehicles. But if that's not enough for you, when Blackbird achieved its record speed of 27.7 miles per hour in a 10 mile per hour tailwind, it was still accelerating. And we know this because there were multiple GPS units in the car and wind speeds which were measured at the height of the propeller at multiple locations. The highlighted section shows the 10-second measurement period over which the record was set.
The vehicle is operated in a gusty wind. Initially, you have the wind speed exceeding the car speed, but then the wind speed is not constant. The wind speed drops, and the car moves by inertia with deceleration for a while. The wind in the video is measured at the height of about a meter or meter and a half, but the propeller goes to some 3 meters above the ground.
They've achieved up to 2.8 times wind speed. That feels much higher than what is possible here, unless the wind had picked up and then spontaneously sort of dropped.
Very, very good question. Okay, if you're going for the record, you probably will do many attempts. You will be sampling that gusty wind over and over and over until you set the record, right? That's how you set the record. And on one of those occasions, you will get a nice strong gust, which is 3 times the ebb that comes after it, okay? And that's when you will clock the record, and that's where that 2.8 factor will come in.
But now we've run into the divide by zero problem that Professor KUSENKO warned us about. When the speed of the car is exactly equal to the speed of the wind, it seems like the propeller can provide infinite force.